Right, I guess we should begin. Fundamental theorem of So we covered fundamental theorem of calculus, and let me remind you what's the statement. So if f is defined on the interval AB to R is continuous, then f of x has an antiderivative of the form capital F of x equal to the integral from a to x of f of t dt. Now this t is what you call a dummy variable. You can replace it with pretty much any other letter. So it could have been written as the integral from a to x of f of u du. The only exception is that this variable is not to be x. So example, if little f of x is equal to cosine of x squared, capital F of x will then be written as, for example, the integral from, you can select this number to be any number in the domain of cosine x squared. So it could be 0 to x of cosine of t squared dt. Okay? And what it means is that if I take the derivative of this uppercase f, I get cosine of x squared. Many antiderivatives can be then obtained this very simple way. So for example, if I take f of x to be x squared, then I can define capital F of x to be the integral from 0 to x of t squared dt, and this is a correct antiderivative. In other words, if I take capital F prime x, I get x squared. You might know another formula for this f of x. Actually, capital F of x has a simpler formula. Namely, capital F of x happens to be simply 1/3 x cubed. Okay? So sometimes you are able to come up with a very simple formula for the antiderivative that does not involve the integral sign. And sometimes you don't have anything in your toolbox to create such a simple solution. So for example, in this case, in the case of cosine x squared, this is your best representation for the antiderivative. You are not familiar with any better representation for that antiderivative. Okay? Now, let's try to understand this theorem just once again. It's very simple if you understand this by drawing. So what's this idea? Why does the function have to be continuous? What's the idea of a continuous function always having an antiderivative? Again, idea behind fundamental theorem of calculus. So if you look at the graph of the function f from a to b, I decided to draw this graph to be just of a curve above the x-axis, but that's not necessarily the case. We don't have to have this as the requirement. So this function, so this is the t-axis, the function f of x will just cut at a and make a cut at x. So f of x is slice of cake function. So more precisely, this is area of a slice of cake from a to x. Okay? Now, what's the clever idea? Why would you consider such cake slicing functions? The thing is, if I make a slice very close to x, in other words, at x plus h, then this this is the region I get by what? So this region here that I colored yellow, what do you describe it as in terms of f again? We went over that. What is this area here? What is A? How would you request for this slice? How would you measure it using this slice of cake function? Yes? Exactly. So this would be, first of all, in terms of the cake slicing function, this is simply f of x plus h minus f of x. Correct? So in other words, this is saying take the slice from a to x plus h, subtract from it the slice from a to x, and that gives you this difference. Now, what does this formula begin to look like? It begins to look like the derivative, right? So you see, this formula begins to look like the derivative. And as you mentioned, you can express this as the integral from x to x plus h of little f of t dt. Correct? That's just the expression of it. Now, if I pull this shape out, let me try to draw this shape. Here is that shape that I have area for. Correct? what is this length over here? Y, and in particular, if we look at this white curve, here this white curve is y equal f of x. And this is situated over x. So the height is f of x. The height is f of x. Do you see that? Now, the shape that I created is not a rectangle. Do you agree? But it is almost a rectangle. If h is pushed to 0, look what happens when h is pushed to 0. So the wall, this rectangle would be thinner, and here for smaller h. So this is for yellow, let's call it h1. Let's see what happens when I select a much smaller h. We'll call it h2. Do you see this? Look at the shape. It resembles a rectangle much more nearly. Correct? So what you can then say is that this area is essentially similar to the area of a rectangle whose height is f of x. So this is essentially the same as f of x times h. And of course, you say for very small h. For very small h. Do you see that? Right? So first, the idea that I'm trying to show you is it's merely a visual proof, just merely an explanation of why that should happen. So therefore, if I calculate the derivative f prime of x, of capital F, that is limit as h goes to 0, h is becoming really small, of f of x plus h minus capital F of x divided by h. And that is limit as h goes to 0 of pretty much this quantity, right? So f of x plus h minus f of x, just looking at this picture, looks like the area of a rectangle for very small h. So this is limit as h goes to 0 of f of x times h divided by h. And you see what I'm using? I'm saying that if h is very small, the cutoff shape is nearly a rectangle, and the height of that rectangle is nearly that edge at x, f of x. And its width is always h. However small I take the h, its width is going to be estimated as h.
Why are you dividing it by h?
Where am I dividing it here by h?
Yeah, because you're finding the area.
Because I'm finding the derivative of this function. I created a function and I ask, is it differentiable? When I ask, is it differentiable, I consider capital F of x plus h minus capital F of x and divide by h.
So this is the antiderivative.
So this shows that capital F is an antiderivative because you see through this construction, I can see that when I take the derivative of this function, I get the curve. Okay, so the clever observation is to see that so the derivative of the area is the curve. Why? Because this curve, if it's continuous, it's going to represent height of the rectangle if the rectangle is very narrow. You see, basically, if I draw this area, if I make this area very, very small, it's like the curve times h. And that gives the idea that if we construct a function that creates areas under the curve of this form, we will get derivative to be this. Make sense? You have to, by the way, when you do this, try to draw those pictures and think about them and try to see that you understand this idea. So h's can cross out, and therefore the answer is little f of x. Okay? So then a few technical remarks about this theorem. So questions? First question is, why must the function be continuous? Why? It's not, by the way, true that it always has to be continuous. You can relax those conditions, but for our purposes, why do we assume that f of x is continuous? In other words, could I take arbitrary function if in other words, if f of x is an arbitrary function, if f of x is an arbitrary function, would capital F of x equal to the integral from a to x f of t dt satisfy f prime x equal to little f of x? Thank you. You understand my question? I'm trying to make you see what's happening here. Why did we assume it's a continuous function that has antiderivative? What if I take some function that is not necessarily continuous? Will I have f prime of x equal to f of x? Yes?
Then the slice wouldn't exactly, because it would have a space and you wouldn't know how much of that space is missing.
That's wonderful. So one thing is, you see, what do you assume here? Here is what you should try to visualize, right? Here is where the argument for the fundamental theorem of calculus can be built around, right? We have this slice, and we are sliding one of those walls, right? And pretty much this yellow region consists of, you can think of it as consisting of multitude of vertical lines. So you have this is the rightmost line, and this is the leftmost line, and you have many other lines in between. If I have a continuous function, what happens if I slide this right wall towards x? What's happening to the vertical lines? What do they become like? In this case, they are becoming bigger, but in general, no. In general, no. In general, if I take this line and I have it basically, I have it narrowed, those right lines become more and more like the left line. You see, look at it. They gradually morph into the same size, roughly, as that white line. And that happens when we have a continuous function. If we don't have a continuous function, that might not necessarily be the case. Okay? So let me give you an example of what can happen if our function is not continuous. Okay? So example, suppose that we have f of x equal to sine of 3x over x if x is bigger than 0, okay, and it is equal to 7 if x is equal to 0. Okay, we have this function. So let's construct capital F of x. So let's say that capital F of x is the integral from 0 to x of the function f of t dt. Okay? Let's try to see what's happening near 0. So if I take let's calculate first of all this quantity. What is limit as h goes to 0 of the integral from 0 to h sine 3t over t dt times 1 over h. And let's say h approaches to 0 from the right. Let's see if you can see what this limit is. Again, no computations are necessary. So do you recall what this expresses? So we have from 0 to h, 1 over h, sine of 3t over t. So we learned last lecture that this is expressing, without the limit, the average of this function from 0 to h. So what this is limit as h goes to 0 plus of the average height of the function f of t over the interval from 0 to h. Now what would that average be? So at 0 the function is defined to be 7. So at 0 the function is 7. Now what is the function like when I am very close to 0? So notice h is going to 0. What's the function like? If I push h towards 0. Can you see that? Here is your function, sine of 3t over t, and 7 at 0. What's going to be this like? What is this going to be like? Well, not quite 1. What is sine of 3x over x? So if h is very small, x is really smaller than h, right? So sine of 3x over x is approximately what number? 3. So in essence, what you would see if h is very small, you would see that that all the altitudes, they fluctuate within 3, very close to 3. So what is the average? So there is 1, 7, and multitudes of things that are like 3. What is the limit going to be like? 3. So this is going to be 3, and it's not equal to 7, which is f of 0. In essence, you see that what I'm trying to show you is that if it's not a continuous function, the average is not necessarily going to be like the value at x. It could be an outlier, right? So what can happen is this, in terms of a non-continuous function. So what you have is this area This is not close to f of x times h, because this is f of x times h. It's an outlier, you see? So this area should be if this region is very small, it's like this length of this wall times h. But if the function is not continuous, this f of x does not represent the wall, the left wall. Does it make sense? No? All right.
Can you also say that it has to be continuous because in order for it to be a derivative, doesn't a derivative have to be continuous?
If a function is differentiable, no, so here it is. This capital function, capital f of x, if differentiable, has to be continuous. But the derivative does not have to be continuous.
No, the function of the derivative has to be continuous in order for it to be a derivative.
So here we have to be careful. This capital f of x, if it's differentiable, you see, just integrating any function f does not assure us that the function we obtain is differentiable. If we integrate a continuous function, the result is differentiable. We saw it. We proved, roughly speaking. That's the fundamental theorem of calculus. This capital F function is differentiable. When it's differentiable, you know nothing about little f. It doesn't have to be differentiable or continuous. The differentiability of capital F does not imply differentiability of little f or continuity of little f. Okay.
The f of x does have to be continuous.
Okay, here is what I tried to say. That's when you have to really think about it, draw those pictures, right? If I am dealing with a continuous function, if little f is a continuous function, then capital F will be a differentiable function. Does that make sense?
Yeah.
And what would be the derivative of that capital F?
Little f.
Little f, exactly. You understand what happens? If I am picking any continuous function, no matter, don't worry if it's differentiable or not, that doesn't matter. Pick any continuous function and do this to it, create capital F out of it. This capital F will be differentiable and its derivative will be little f.
Which will be continuous.
Which, yes, by default we picked a continuous function. So yes, it will be continuous, okay? But this example shows you that here this function is mostly continuous, but it's not continuous at 0. You see, this shows you that if you try to do this process, apply to this process to this function, the results are not going to be giving you the derivative which is equal to little f. Make sense?
So what does that mean? Does that mean it's like not, it's voided, or is it still irrelevant?
What's irrelevant?
I mean, so we have a function that's little f that's not the function of f of.
So we have little f, and little f is not a continuous function. You see there is jump at 0. So at 0, this function should be equal to 3, but then we have a jump to 7. So this function is not continuous at 0.
Right. So what does that mean for this answer? Is that answer valid, I guess?
The answer is that when we apply this limit process, we will not get, actually this capital F will not even be differentiable at 0. This capital F for this function will not be differentiable at 0.
So are we don't assume that f of x, the little f of x is continuous?
Well, we cannot assume that because it's specifically not continuous. You see at 0 it's not continuous. So I cannot assume it's continuous because I see it's not continuous. Little f is not continuous. I try to apply this process, and the process will fail for some non-continuous functions.
Okay. So I guess what's the answer to this question?
It's an explanation. Not an answer.
So the answer to this question, is look at the proof carefully. when you do, you should see the hypothesis of continuity at work. Okay, make sense? I hope. I mean, ask me billions of questions and stay in office hours after this is over. I really want you to get this idea. It's actually not too complicated, right? It's very visual, in fact. Okay. Here is my second question. Again, I'm worried to waste time on it, but I just wonder if you notice, why do we switch to t? Why do we switch f of x to f of t? Why do we do that? I mean, why not just, in other words, why not That's what I want to ask. Right? What did I do when I was finding antiderivative? Look at it. I did not write integral from 0 to x sine of 3x over x. I wrote sine of 3t over t. Why did I do that? Why did I switch the independent variable from x to another letter? It could be any other letter, but it cannot be x. Why do I do it? So this can be answered in several ways. One way is doesn't seem to be making sense if we keep x. And here is what I mean. So this is supposed to be a function. So what is this function at 2? This function at 2 will then be the integral from a to 2 of the integral of f of 2. Because everywhere I see x, I should replace it now by 2, right? Times, if dx is not a separate symbol, d of 2. Right? If you treat x as a separate symbol, this would be f of 2 times d of 2. So what is that? Here I'm assuming dx is treated as two symbols. Okay? So that's one way to just try to dismiss this problem, is just, you see, everything breaks down. I don't really get an integral. Every time I replace an x by a number, I have to do this replacement for all instances of x. And then the result, d of 2, what is that at all? Okay? I don't like this explanation, right? So I will say b, right? Because, I mean, let's say this makes sense, because d of x will not be treated as two symbols, right? So dx is not a place where you substitute, it's a different symbol altogether, right? dx is just a different meaning altogether. May I erase this part? So the explanation B is a little bit better, I think. B, so here dx is not d and x, okay? So let's try to consider the two functions. Consider f of x to be equal to the integral from a to t to x, I'm sorry, of f of t dt versus g of x, which is the integral from a to x little f of x dx. Okay? Let's try to consider what's the difference between them. So in the first case, here is the t-axis, here is whatever y-axis may be. So here is the curve. Let's draw maybe a simple curve like a parabola. This is A. This is B. And what's the meaning of f of x? So if I draw the meaning of f of x, it means make a slice at A and make a slice at x and calculate the area of the slice. You see what I colored in yellow? This is f of x. Make sense? So that's what this means clearly. If this is the t-axis, this is y equals f of t. This is what I get for the slice. Now let's try to do the same thing for g. I select the same x. What happens now? What region am I coloring? So what's g? What's going to be g of x?
8x.
We cannot get a number. This is just, those are just pure symbols. But what sort of picture am I going to draw for g of x?
Area underneath. Between A and
So in that case, if I pick this x, look what happens. I mean, you can just see what happens here by looking at what's g of 2, for example, right? What's g of 2? G of 2 is the integral from a to 2 of f of 2 times dx. Here is where I don't treat dx as you see. So what is that? F of 2 is not changing over this interval. It's a constant. You see? So for this x, what happens? You see what happens? G of 3 is the integral from a to 3 of possibly a different constant, which is f of 3 dx. So at x, what I have is I have this is f of x. This is f of x, and what the area I'm calculating is for the curve that is completely flat. You see that? If I selected a different x, if I selected, let's say, this value, the area that this expresses just by the mechanism of it would be that area. So it's not expressing the area underneath the curve. It's always expressing an area of a rectangle. One of the sides of this rectangle is f of x. Okay? So if you don't switch the variable from x to something else, you inadvertently communicate something you did not intend, right? This is a rather useless function. You never wanted to calculate areas of rectangles, one of whose vertices is at the curve y equals f of x. What you wanted for this problem is the area between the x-axis and the curve. Does it make sense? All right. So the fundamental theorem of calculus allows us to find areas between curves with great simplicity. So let me show you how that works. And again, I might try to explain it. So example. Suppose you were asked to do the following. Find the integral from, let's say, 0 to 3 of x squared dx. Okay? So you would have done it using Riemann sums. Using Riemann sums, this would have been do you still remember how to set up this integral? There would be at least one question when you have to do it directly using Riemann sums. So you would have had to say limit as n goes to infinity. Can you tell me what I should write here? Summation from where to where? K equal to 1 to n of what? Right. So what do I write here? So change of x is 3 minus 0 over n or 3 over n. What else do I need to put in here? Well, f of x is x squared, so what do I do with it? Remember what this means. This means I construct rectangles. The width of the rectangle is dx, very small delta x. The height of the rectangle at x is x squared. So in particular, when I do n goes to infinity, I approximated the area by n rectangles. What's the height of the kth rectangle? 2x. No, it cannot be 2x. It has to be in terms of something squared. What do you do? Well, you take k times 3 over n, and you square it. Guys, make sure that by Friday you are very comfortable setting up Riemann integrals and doing Riemann integrals. Okay? So we can do this, and this is tedious. So we now have a shortcut. I'll first give you the shortcut, even though I don't like it without you understanding it, but let me show you how the shortcut works. So fundamental theorem of calculus allows us to have a shortcut. Fundamental theorem of calculus shortcut. And the fundamental theorem of calculus shortcut is that x squared has 1/3 x cubed as antiderivative. Okay? And take any antiderivative. 1/3 x cubed is just one of them. Take any antiderivative, and then what you observe is that the integral from 0 to 3 of x squared dx, this is simply 1/3 x cubed. Draw a line from 0 to 3. And what this means, it is just 1/3 3 cubed. So you take this expression, evaluate it at the top number, minus the same expression evaluated at the bottom number. Okay? So what you end up getting is that the answer, which you can verify using Riemann sums, that's one good way to train yourself, right? Use the shortcut, then see if you can get it the long way using Riemann sums. So that would be 3 squared or 9. So the answer is very quickly 9, without doing this very long, tedious procedure. That's how the fundamental theorem of calculus works. Let me give you more examples of that. Well, 3 cubed is 27, so I canceled with 1/3, right? So it would be 9. Example? So you understand that this is the link to antiderivatives. I'll try to again explain why this link works. But the thing is, area under the curve and antiderivative are very fundamentally linked. So let's try, and many questions, in fact, if you try it by Riemann sums, you will never get the answer. It's just going to be overwhelming. So let's try something like this. Let's try the integral from, well, let's say from 1 to 9 of root of x dx. Okay? Solution. You see, so by the way, finding antiderivatives can, because there is this fundamental link between, instead of just drawing this arrow, I can just represent antiderivatives as follows. So first of all, find so this just means find antiderivative. The reason for this notation is to remind you that there is link between area under the curve and finding antiderivatives, which we saw. Okay? So what would that be? So we have that the integral of root of x dx is the same as the integral of x to the power of 1/2 dx. And what would that be? Remember this guessing game? X to the 1/2. X to the 3/2. 2/3. And you can say plus any constant, right? In general, if you are asked a question like this is what they want from you, right? They want from you an antiderivative. And the implication, here is the implication to the shortcut, is that the integral from 1 to 9 root of x dx is the same as 2 over 3x 3/2 evaluated from 1 to 9. Okay? So what do you get? You get 2 over 3 parentheses 9 to the power 3/2 minus 1 to the power of 3/2. Okay, so what is that? This is, you don't really need to continue. For me, that is enough. But this is 2 times 3. This is square root of 9, which is 3. 3 cubed is 27. So this is 27 minus 1. Okay? Good? You can write it 26, whatever. Right? So this is the answer here. So let's try another question. All right, so what do you do if it is from pi over 6 to pi? And here we have sine theta d theta. So what do we do? What's the antiderivative of sine? So what you do is very simply minus cosine of theta pi over 6 to pi. What's cosine of pi? Negative 1. So what you get is negative minus 1, and then minus, what's cosine of pi over 6? Right. So because there is a negative here, so it would be negative square root of 3 over 2. And altogether what you get is 1 plus root of 3 over 2. Okay? Let's do a few more examples. So what do you do if you encounter something like integral from 0 to 1, u plus 2, u minus 3, du? Suggestions. What do I do here? Distribute. So remember that I want to find an antiderivative of u plus 2 times u minus 3. Unfortunately, there is no nice product rule. There is nice sum rule, but there is no nice product rule. So common mistake is to find the antiderivative of u plus 2 and multiply it by the antiderivative of u minus 3. That's incorrect. So what you do is 0 to 1. Distributing it, it would be u squared minus u and minus 6. So what do we get when we integrate this? And then we write this line and write 0, 1. Okay? And then we just, you can see if you plug 0, it all vanishes. So the answer is 1/3 minus 1/2 minus 6. Okay? You can simplify it if you want to, but good enough for me. Let me give you 2 more examples, and then we'll move on. So let's say very quickly integral from 0 to pi over 4 secant squared of t dt. What do I get? All right, so either you recognize it or you don't. What's the antiderivative of secant squared? Tangent. Secant plus tangent would be the derivative of secant, right? We go in reverse. So the antiderivative of secant squared is just tangent. So this is tangent of t, and we evaluate from 0 to pi over 4. And the result is, what's tangent of pi over 4? 1. So this is 1. What's tangent of 0? 0. So the answer is simply 1. Okay, let's do another example. Let's suppose we have integral from 1 over root 3 to root 3 of 8 over 1 plus x squared dx. What do we do now? All right. Do you recognize what should be the function here? It should be 8 times tan inverse of x evaluated from 1 over root 3 to root 3. Yeah?
If we don't recognize that, can we just use the other thing?
What other thing? If you try Riemann sum, you will not succeed.
And we have to memorize that?
Oh, I don't like the word memorize really, right? I suppose there is some memory when you take but what you do is you begin to recognize your functions. They're your friends. So tangent inverse should be your friend. You should know how the derivative of tangent inverse looks like, and then how to go back.
Tangent inverse, what else?
Well, all the inverse trig functions, logarithmic functions, algebraic functions. You know, we haven't really covered many functions. Think about it. Polynomials, easy. Rational functions, just ratios of polynomials, right? They're actually, you deal with them sometimes.
You're going to be including this in the final?
Of course.
Professor, you should tell them that the clue is the square root of 3 or 1 square root of 3. That gives you the clue that there's going to be some trigonometric function.
It does, but sometimes you don't have those bounds. So you just might have just the integral of this. What gives the clue is 1 over 1 plus x squared. Okay, so what's the result? So we have 8. I'll put it in parentheses outside. And I have tangent inverse of root 3 minus tangent inverse 1 over root 3. And then I want to know what's the result. So if you don't remember the values, you can draw yourself a triangle. It's a right triangle. And you know that there is, you should know this triangle where if this is pi over 3, this is 1/2, this is 1, this is root 3 over 2. And this missing angle is pi over 6. Okay? We can go again. I went over how to construct those triangles. I can do that again in Office if you want to see that. So what you see is that tangent of pi over 3 is equal to root 3. And tangent of pi over 6 is equal to 1 over root 3. Okay? So the answer here is, since this is, so I just take inverse, right? So inverse tangent of pi over 3. So what I have here is 8. And the first number is what? Minus pi over 6. Okay? So one more example. Suppose you have the integral from 1 to 2 of v cubed plus 3v to the power of 6 divided by v to the power of 4 dv. So first of all, this function we're integrating is rational, right? It looks like maybe we need to do something to make it simple. There's just one nice trick. Separate. So it's 1 to 2, and what you do is this is v cubed over v to the 4 plus 3v6 over v to the 4 dv. This is from 1 to 2. V cubed over v to the 4 is 1 over v plus 3v squared. Correct? What do we do with that? What's the antiderivative of 1 over v? ln v. To be more precise, it is ln of absolute value of v, which it doesn't matter. Absolute value is not going to matter here. Plus, what's the antiderivative here? V cubed. And this is the expression that you evaluate from 1 to 2. So plugging in 2, what you get is ln 2 plus 8 minus ln 1 plus 1. Ln of 1 is 0, so what you get is ln of 2 plus 8 plus 7 exactly. Ln of 1 disappears to 0. Ln of 1 is 0. So it's ln of 2 plus 8 minus 1. So it's ln of 2 plus 7. Okay? So you can see that fundamental theorem of calculus gives you a very nice way to, in many cases, at least in the cases that we are presented here in this book, to avoid doing this tedious Riemann sum, right? To not try to calculate the Riemann integral by taking this complicated limit. But of course, I mean, we will try. Hopefully today I'll be able to explain to you why it works. If you don't know why it works, you can be easily caught and actually make a mistake. So just be careful. Here's what I want to say here. Be careful. So for example, suppose that what we do is let's integrate from minus 1 to 1 the function one over x squared dx. What would you do? So let's see, we have this procedure, right? So this is from minus 1 to 1, x to the minus 2 dx. Correct? And then what? What's the antiderivative of x to the minus 2 or? So that would be x to the minus 1 with a negative. And you would try. Again, I'm hoping I'm not leading you. You agree with this? Yes? Yes? I mean, if that's what I asked, will that be what you would be doing? Mom, it's x to the squared. So is that what you will be doing?
Yeah.
Yeah, okay, good. So then, what do we get? I can factor the minus 1 outside. So what I have is 1 to the power of minus 1 minus 1 to the power of minus 1. And the result is minus 0, correct? This is 0. So the result is 0. You all see this is 0? Is this the answer? It is absolutely wrong. Because you applied something without knowing, right? Here's a shortcut, let's just do stuff like this, right? You try to use an appliance without knowing what to do with it. It's like, here's a toaster and here's a bathtub, right? You drop it into the bathtub. That's not what the toaster is designed to do. Why is this wrong? Well, let's try to look at the picture of 1 over x squared.
Did you do like Riemann's?
If you want to, right? But
I mean,
you can do a lot of things, right? Well, so here is the shape of the graph. It looks like a volcano that has no peak, right? Sometimes they call it Gabriel's horn, because Gabriel has this very long trumpet, I guess infinite trumpet, since he is an angel. This is 1. This is -1. First of all, what does it look like the area to be? I mean, does the area look like it could be 0? You see, this is area under the curve because the graph is above the x-axis. Does it look like it could be 0? No. So it looks like something failed. What failed? The function was not continuous at 0. Remember, fundamental theorem of calculus works for continuous functions. It actually works for other types of functions, but for our purposes, we just say that it only works for continuous functions. So you see, this trick works based on the fundamental theorem of calculus, which itself works under the assumption that we have a continuous function. So it fails here. You are using it inappropriately. OK. So I'll try to explain later. Let me just, before that, try to explain something that you are interested in because it's on your exam. So calculating derivatives related to fundamental theorem of calculus.
Professor,
Yes.
question. So it doesn't work because it's not continuous?
It doesn't work. Well, you cannot apply this trick because the function you're dealing is not continuous. It's not continuous at 0. When you're integrating a non-continuous function, you might create yourself lots of problems. Basically, when you deal with functions like this, those are rogue functions, and the integral is called improper integral. There is a way to deal with that and to analyze such integrals, but that you might learn in your second semester calculus. All right, so calculating derivatives related to the fundamental theorem of calculus. So let's try this example. Example, find d dx of the integral from 0 to x of cosine of t cubed dt. What's the derivative of this? So that's example A. What's the derivative? So answer. So nothing to worry about. The function we're integrating is continuous everywhere, in particular continuous from 0 to x. So if you look through the argument of the fundamental theorem of calculus, should work, right? So what's the derivative? What is the answer? Cosine of x cubed, right? That's pretty much just doing, that's what it was meant to do, right? Functions of this form, they were meant to be antiderivative. So this is cosine x cubed. So wonderful, that's correct. Let's try B. Now, suppose that what we're dealing with is, we are dealing with a new function, g of x. Now it's the integral from 0, not to x, but to x squared of cosine t cubed dt. What is g prime x? see something is different, right? This is x, this is x squared. How do I deal with this new problem? Wonderful. Chain rule, right? So you look at this thing and you say, oh. So first of all, wishful thinking, you are going to say, you can afterwards do it faster, but let capital F of x be the integral that you would be happy with. Okay, this is the integral you would be happy with. And then you define p of x to be the function x squared. And then you observe that the function g of x is simply capital F that has eaten p of x. That's why chain rule comes to mind. Do you see that? It's combination of the regular function that you now know how to deal with x squared. So what's the derivative then? The derivative g prime of x will be the derivative of the outer function with p of x in its belly times p prime x. So what is the derivative of the outer function with px in its belly? That would be cosine of px cubed times p prime x, which in particular is cosine of x squared cubed times 2x, which is therefore 2x cosine x to the power of 6. Okay? So let's try to see what happens. What do we do in general if I have, in general, if I have g of x to be the integral from some number a to some function k of x of little f of t dt, what's going to be the derivative g prime x? What's going to happen? So I see integral from a to some function that is not necessarily x. What do I do? Well, I do chain rule. So by the chain rule, this is little f. What's in its belly? Times k prime of x. So for example, here is a. So what's the derivative from, I don't know, from -5 to tangent of x of e to the root of t, or root of u, du. What's going to be the derivative? Well, very simply, based on this formula, it's going to be e root tangent x times what? Okay, does this make sense? b. What's the derivative from 2 to 3x cubed of v sine of v dv? Ready? Very simple. What do we write? We plug in 3x cubed sine of 3x cubed times what? 9x squared. And you can simplify it, but it doesn't matter, okay? So this is what you do. Now suppose I'm going to make it a little bit harder. So what do we do?
Why didn't that go to cosine?
That's the thing. When you take the derivative of, look at this formula, right? G, integral of any function. What you have is you just have this function eating the expression on the top times the derivative of the expression on the top. Be careful, right? This is not the derivative of cosine. This is the derivative of this new type of function that we created. So what to do? Well, what is g prime x if g of x is now equal to the expression k of x on the bottom, a on the top, f of t dt. So now k of x is on the bottom. What do you do? Exactly. So you remember we learned the property of integrals. So we have that g of x is the same thing as minus the integral a to k of x. I can multiply by minus 1 and the k will move to the top of f of t dt. And g prime of x will then be equal to minus f composed with kx times k prime x. Okay? So example, so let's say I'll just give you one example. So let's say we calculate ddx of the integral from tangent x to minus 5 of e to the root u du. The derivative of that is simply minus e to the root tangent x times secant squared x. Okay? That's how it works. So make sure you practice. There will be examples like this on the exam. Let's consider the most general situation. Example. What is g prime x if g of x is the integral from ax to bx? So two functions, one on the top, one on the bottom, of f of t dt. So what you can do is you can observe that g of x can be written as the integral from ax to some number c of f of t dt plus the integral from c to b of x f of t dt, which is the same thing as the integral from c to b of x f of t dt minus, I can switch it so that it's on the top, minus c to a of x f of t dt. And that means that g prime x is just going to be f of bx times b prime x minus f of ax a prime x. So let me give you an example of how that works. So suppose that g of x is equal to the integral from x to x squared of e to the t squared dt. What's the derivative? So here is what I do according to what I just verified here. So make sure that you can verify this general formula. So according to this, I take this function e and I plug the top function. So it would be x squared squared times the derivative of this function, which is 2x. Are you with me still? What do I do next? Minus. And now I do what? I have e. And I put the bottom function, it happens to be x, times what's the derivative of that x? It's just 1. So altogether I get e to the x to the power of 4 times 2x minus e to the x squared. Yeah, by the way, don't forget, if you haven't done so, to put your exam in my bag. Okay, good. So let's give you another example. So again, guaranteed that such a question is on your exam, right? One of such questions is on your exam. Make sure that you train it. One guaranteed question is calculate the integral using Riemann sum. One is like this. A few examples where you need to set up the integral. Have you seen the third practice exams? Have you seen them? Yes. Make sure you really, really see them. Okay, another example. Suppose that our g of x is the integral from cosine x to sine x of ln 1 plus 2v dv. I want to find the derivative. What's g prime x? Quickly. Evaluate it very, very, very quickly. So what do we get? No, no. There you go. ln 1 plus 2 sine x times what? Cosine x, yes, then minus ln 1 plus 2 cosine x times easy, very quick. Okay? So a few other questions just to see what's your intuition. So example doesn't have to be related to what we just did. I just want to see how ready you are. So find the integral from minus 4 to 0 root 16 minus x squared. Use any way you can. Huh? Anything you want. If you are told find this expression, it means just use any tool in your toolbox. No matter what, just find it. Solution. So somebody already mentioned what's the easiest thing to do here is to recognize that we're dealing with a circle, but to convince me what part of the circle are we dealing with. Where is that part? What's the radius of the circle? Yes. Where is what part of the circle? Huh?
Bottom.
No, not bottom, because you see that this is a plus, right? So it's not the bottom part. What part? X is from minus 4 to 0. Where is that? It is which quadrant? 1, 2, 3, or 4? In quadrant 1, do we have x equal to minus 4? It's quadrant 2, exactly. Here is minus 4. The fact that it has a positive side tells us that what part of the circle are we dealing with? 1/4 of it, right? So what we have is 16 divided by 4 times pi is this area. Okay? Or 4 pi. So let me ask you a few more questions. Okay, don't keep yourself here. Find the integral from minus 3 to 3 of sine of x cubed dx. Anything you want. How do we find this integral? All right. So here is what you can try doing. If you're going to try to find antiderivative, just try to do this regular procedure, you are going to be miserable and unsuccessful. What you do here is take f of x to be sine of x cubed. And then observe that if I take f of minus x, that would be sine of minus x cubed, which is sine of minus x cubed, which is, sine is also odd, so it's minus sine of x cubed. So the function is so the function is odd. So this is minus f of x. F is odd. Now if it's odd, and notice there is a balanced interval, minus 3 to 3, what must be happening to this region? So there is going to be part of the curve. I don't even need to do it precisely, but I know odd means symmetric to the origin. So part of the curve is here, and the integral from 0 to 3 will give me some area A. What would the integral from minus 3 to 0 give me? Because the heights are negative, it will give me minus A. So the integral from minus 3 to 3 of f of x dx exactly is A, or minus A plus A, which is 0. That's because of two factors it's 0. Because the left interval and the right segment of the interval are balanced, right? They're exactly the same size. And because the function is odd, so you have, it's either, I mean, it doesn't actually matter. I just know that it's positive over the positive part of the x-axis. But in essence, what matters is that there is a reflection to the origin. If you have in one side positive area, on the other side you have negative area. Does it make sense? Let me ask you one more question. Example, find the average. Average of f of x equal to x squared over the interval (0 to 2). So I want to find the average height of this curve from 0 to 2. In other words, what am I averaging? I take all those lengths, and I want to calculate what's the mean length. Right? So here it's 0, here it's 4, and you have a bunch of lengths in between. I want to know what's the average here. What do you do? So f average. No. Well, it would be, again, you should derive those formulas, right? Otherwise, you will forget. It's the integral from 0 to 2 of x squared dx. We derived the formula for that, right? You should derive it. And something is missing. What's missing here? Times 1 over 2 minus 0. Or over, so I'll write over 2. You should know it's 2 minus 0. Okay? What do we get? We get 1/2 times 1/3 x cubed. And from 0 to 2. So the answer is 1 over 6 times 2 cubed, or times 8, which can be reduced to 1/3 times 4. So it's 4/3 is the average. Okay? So the height on average here will be 4/3. All right. So we will continue on Thursday, and pretty much, you see, you have to know this material. you should know it's called now. Interested in understanding it, you should try to understand why this fundamental theorem of calculus allows us to do this shortcut, right? That's the interesting part. Everything else is just stupid calculation. Right? If you just say, so if you study like this, here, I memorized the formula for the average, and then I'm very sad for you. All right. So good night if you're not staying. Good evening if you want to stay longer. Yes, what's the question?